Okay, so hello everyone. I hope I'm audible. So, we'll start with this lecture. 4 weeks right. Familiarize ourselves with some items, item choice. Let's mention them along. Let's start.
So you are inaudible.
By the way, am I? Oh. Hello. I'm still not audible. Hello. Am I audible? Okay. I guess I'm audible the whole time. So we'll get on start with an analysis before we start with the basic concepts series. So that's what I'll be speaking into. Numbers, the numbers, let's get suppose you have a sequence of natural numbers, 1, 2, 3, if you keep all the this is compacted as things and which we can care of this let's explain would that be clear? So that's how we write it. Say a sequence extends inside a set S. Here, set of attributes. All say all the terms of the sequence are drawn from a set S. The sequence is set to inside S. So let's see what's the common definition of the sequence. The sequence is a function from natural goes to real numbers. Okay, transfer number to a set S. It's just a project. Remember the don't I'll try to see it does one compact with that. So it's one it's only set one and the above is all that sets it. So, it depends. It's sequence gradually gets towards the number. The value that is it's the value the wire and the x-axis. Let's take the example of this. Right? So it's a particular value of the limit of this sequence. So there's a products that we can implement for about natural storage. There's something called the subsequence of this. So that's very natural, right? Subset of natural number. So if we take this subset of then call it's of suppose there is phi that has natural number. You just some of the natural order. architecture, both the state and both the six, both the city, and the development. You also can almost wide. Three subsequence. To draw the values of its parent sequence is supposed minus one, one minus one. This new sequence is like contains some of the items of the initial sequence, not all, but they are both infinite. This is subsequence. Then let's see how what is the definition of the limit of the sequence, right definition. So we say xn converges. Okay. Only for all and only for all epsilon greater than 0, there exists capital N natural number. It's natural number capital N is that for all n greater than that natural number. We have a mod or the difference, the absolute difference between L and xn is less than or equal to L epsilon. It's not good epsilon. So if you have a better understanding of this definition, on top suppose this is a sequence. It is direct index and the values are put in the y-axis. So they kind of appear randomly here. Try to represent the general sequence. Suppose the limit L is this one, y equals to L. So after some time, with all values of xn thereafter, y inside some epsilon boundary around plus line L, then you can safely say L is the limit. And finally, the epsilon is actually, you can make it as small as possible. So that's why you have said for all epsilon greater than 0. This n is actually dependent on the epsilon that we pick. Epsilon is not 0 because otherwise, yeah, like having 0 means the sequence after some time will be equal to that constant value L, which is not always possible. It can be possible for some sequence. Let's see the perfect sequence under convergence limits. Say suppose the sequence x equals 1 minus 4 plus 1. So how to show the first direction? So the x converges to 0. If you plot it with the reference software or something, you'll see this kind of converges towards the line x equals to 0. Let's see how to do that. So according to the definition, you need to show this reducible for all epsilon. So we have to arbitrarily pick epsilon first. So it's epsilon greater than k. So now that we have our epsilon, we have to find the n, which is dependent from can be dependent on many things. It can be dependent on epsilon. It's always dependent on xn, but it's not dependent on n and smaller. After all, you have to be able to see something like L is zero here. If that's what you want to make it. So zero minus epsilon, which equals actually less than or equal to epsilon. So make it quick. Let's replace epsilon there. Now we can go in the other way around also. What exactly is 1 by e square plus 1 less than? So if it's less than we remove the 1 from the denominator, which we have to get something that is larger. Where d is equilibrium. This in turn is smaller than 1 by x, which is much more. So x square is that is largely smaller than n square, with both facts increasing. Since n is increasing, so the smallest value of n, for which smaller than epsilon, we can take that value as to exist. So suppose 1 by n by capital N less than epsilon, we will be saying 1 is less than n epsilon. So, we will reach the epsilon with 1 by epsilon. Epsilon is a positive real number where 1 by epsilon is a term is very small and 1 by epsilon is very large, otherwise it's kind of small. So this is also real number. So we can take the n to be equal to ceiling of 1 by epsilon. Right. Now we can say, let's say, so it says there exists an epsilon. So we can take, we have fixed epsilon, remember, now we have to define n epsilon terms of epsilon. So we can define to be ceiling of 1 by epsilon, which is an actual number of epsilon is positive. Then for all small and greater than an epsilon, we have every short 1 minus epsilon was 1 by x squared plus 1 less than 1 by n less than 1 by n. Capital N epsilon, which is less than 1 by 1 by epsilon. Sorry. So that's how we prove that the limit is equal. Okay. So here we are able to prove the existence of n using this fact that there exists a natural number n such that n epsilon is greater than 1. Right. So this existence is actually not trivial. So this property of real numbers is called the Archimedean property. So it says so formally it says if x and y are two real numbers and one of them is positive, say suppose x, then there exists a positive integer n. There exists n inside naturals such that y is less than nx. Okay. So yes, this is an axiom, so you can't prove it in that way. There are ways to prove it using other axioms, like Zorn's lemma and axiom of choice. So the proof it goes like this. Let's consider the set A equals to nx for all n in naturals. X is the same x as here. Okay, so uh, now if for all a in A, y is greater than A, so we are assuming this doesn't happen. So there doesn't exist an instance that y is actually less than nx. That means for all a in A, y is always greater than A. So therefore, A is a upper bound. Sorry, y is an upper bound of A. So what is an upper bound? Upper bound is a number. So if you have a sequence S, sorry, not sequence, set S. So if you have a set S containing some real numbers, set of R, if you have a real subset and all the values of S are less than some Y, or you can say like this, S top bar, then S bar is a real, is an upper bound. Very simple. The number that is larger than all the elements of S is an upper bound. The number that is smaller than all the elements of S is a lower bound. But the problem is the uniqueness of an upper and a lower bound. So we can uh, from the continuity of real numbers, you can say the upper bound of real numbers, upper bound of any finite set exists, and for this Archimedean property. So in case of real numbers, real numbers have a property that defines a unique upper bound for a subset S of real numbers. So let S be some subset S, subset of real numbers, and let E be the set of upper bounds. This is a shorthand for upper bound, BDDS. E is a set of upper bounds, then okay, S is not null, non-null. Then E has a smallest value. E has a smallest element. Kind of like well ordering principle. So E has the smallest element. Call it S cap. This S cap is the lowest upper bound of S and is called the supremum. It is also sometimes denoted as sub S. So they all are equivalent ways of referring to the same number or a set S. So yeah, so using that completeness axiom, so this axiom is called completeness. So here we define the set A and X, which is a subset of R, as we can see, since N and X are both real numbers, and it's non-empty because N, X1, X2, X are there, and then say suppose we don't get a such that a is larger than y, then y is an upper bound of a. Then by completeness of R, there exists a supremum sup A of A, which is the lowest upper bound. So we can call so we are calling that a upper bar, right? A supremum. X is greater than 0 from here. So that implies minus x is less than 0. So that implies supremum of a minus x is less than supremum of a. And so we know this is lowest upper bound, right? And anything less than that, like this is less than that, strictly less than a bar. So this can't be a lower bound. So not a upper bound. Sorry, upper bound. Therefore, this has to be inside the setting. No, I mean now. So why is this not an upper bound? That means there are some elements of. So there exists some A star. So my laptop is running out of it. There exists some A star in A such that A star is larger than this value, upper bound A minus X. Let's say that A star is equal to some N star times X. Then that implies N star plus 1 times X is larger than A. Right, so we found a number that, so this is a natural number, since N star was a natural number. So natural number times X, so this whole thing is inside A, but this is larger than the lowest upper bound, A bar of A, which is a contradiction. So what was our assumption? We assumed for all A in AY is larger than A. So that is contradicted. So there exists n natural numbers such that nx is larger than y. That proves the Archimedean property. So we can use it here. let's get back to convergence, limit of sequence. So properties of limits of sequence. Every convergence sequence in R has a unique limit. So limit is unique sequence is convergent real. And every convergent sequence is bounded. That is, every sequence is bounded, is convergent. There is a set from which the values of the sequence are drawn. That set is bounded. Number three is if xn is a sequence is bounded, it can be bounded below, it can be bounded above, whatever it is. In the subsequence, then any subsequence is also bounded. And if xn converges to x, yn converges to y, that implies number one, xn plus minus yn converges to x plus minus y. Number two, xn times yn converges to x times y. Number three, xn by yn converges to y not 0. Requires number. These are the standard limit terms that we can derive from the definition. Okay, so I again show you the first group why the limit is unique. So a converging sequence has a unique limit. We suppose the limit is not unique. So xn converges to L1 and xn converges to L2. L1 not equals to L2, say something. So we have to show L1 is equal to L2, so it come up with some kind of contradiction. So let's see the difference between L1 minus L2. Let's take epsilon to be smaller than that. From the definition of sequence, we can say there exists a unique n epsilon side n, such that L1 minus xn is less than epsilon for all n greater than an epsilon, and L1 L2 minus xn is less than epsilon or m greater than n epsilon. So from these two, we can say L1 minus xn so this difference is actually larger than L1 minus L2 minus. This is from triangular inequality. Right, so from triangular inequality, we can say this happens, and that means L1 minus L2 is the lower bound of twice xn, which is no problem since L1 minus L2 is a constant, non-zero constant. Epsilon can't be greater than this, sorry, can be smaller than this constant. So if we take epsilon to be something like L1 minus L2 by 4, then one get a value of n. So you can't decrease epsilon at middle one. There's a lower one how much you can decrease. So that must not exist. Let's experiment. And there's also something called the lowest, sorry, highest, highest lower bound or infimum. We find similarly like we have a set and then the set that contains all the values, lower bounds of that set. Suppose that lower that the continuity of R that set has a upper bound. Sorry, I mean the largest value. That largest value is called the input. So for all subset S in R, there exists this bar or bar in R such that for all x in S smaller than S. Yeah, by the way, this is not all x, all s bounded below. That is, if you find one lower bound, then you ensure that that lower bound there is a unique, some unique lower bound. If you don't find a lower bound, then you have to prove that it is not bounded. It's unbounded below and be unbounded constant and unbounded on both sides, like that. Monotonic convergence theorem. This is the first theorem of sequence convergence. So any monotonic sequence of sequence which is bounded converges. This is kind of obvious if you think of the sequence that continuously increases but doesn't cross a certain value. then obviously it flattens out near that value. So that is the limit. Right. Next is the strictly monotone sequence. So there are stagnations. Okay, not strictly, it can be less, I mean, weakly monotonic and equalities are allowed. So it's had monotonicity not been a criteria, then we can think of bounded sequences that are not monotonic, like 1 - 1 sequence. The sequence is bounded. It is bounded below by -1 and bounded above by 1. So S bar is -1 and S bar is 1. So it's bounded, but it is not convergent since it is oscillating between these two magnitudes. Going nearer to one of these. So if you fix an epsilon equals to 1/2, then up around this equals 0. So if n equals to 0, epsilon equals to half, then we won't get any value, any n for which things after that get into that epsilon half neighborhood of 0. All the values are outside of this kind of 1 plus 1 and minus 1. Okay, so let's here. So Xn we have a sequence which is monotone. Therefore, if we take the elements, we define a set around that sequence like this. So then S is bounded above by suppose S bar is the supremum. Let me not call it S bar, let me call it sub S. So now see S minus okay, so we have to show this is convergent, right? The first step is to fix epsilon positive, and then we look at the number S minus supremum of S sub S minus epsilon. This number is strictly less than S. I mean, sup S since epsilon is positive. So therefore, there exists some element of S. There exists some Xn in S, such that Xn is greater than supremum of S minus epsilon. So we can rearrange this to write it as epsilon greater than supremum of S minus Xn, and then take a mod like it's already greater than 0, but still not take a mod. This is it. So it's capital. Now, Xn is monotonic, right? So if we reduce n, we will get values, sorry, if we increase n, we will get values that are larger than it. Therefore, Xn plus 1 is greater than Xn, greater than Xn minus 1. That's what we're going to do spread. Therefore, supremum of S minus Xn is larger than supremum of X minus Xn plus 1. Like that. If not to smaller. All of them are positive already since. supremum is the supremum. So when the supremum of S is supremum of S, so it's larger than all entries of the sequence. Epsilon is larger than all of them. That is the difference. So that's how we define the capital M. So for all m greater than capital M, which we picked as so and so, we have mod of supremum of S minus x m. So x small m less than epsilon. This is the monotone convergence theorem. Now we don't need to explicitly show sequence that are monotonic like this one, I guess. So the is we converted xn of 1 by n squared plus 1. I can see it's a strictly decreasing sequence. So this is monotonic and it's bounded below by 0, right? It has to converge. So monotone convergence theorem actually says two things. It's convergent. So if the sequence is monotonic and there is a lower bound, if it's decreasing, then you need a lower bound. If it's increasing, then the upper bound. If that is true, the limit is actually the optimum and the supremum power respectively. You have no increment and supremum to the exact value of the limit. The next theorem is called Weierstrass. This is another theorem that tells us avoid calculating limits from the definition and implying it. So this theorem says a bounded sequence of real numbers has a convergence subsequence. So any bounded sequence of reals has a convergent subsequence. So we will use monotone convergence theorem to prove this fact. So let's take any sequence which is bounded. So bounded sequence. When bounded value means both lower and upper bounded. Actually, one of them would have sufficed. So, we need to prove for the result that any sequences are in monotonic subsequence. So let's extend k. Extend k greater than or equals to 0. Previously it was n greater than or equals to 0. And it's k greater than or equals to 0. This is a monotonic subsequence. And we're assuming that let this be a monotonic subsequence. So why can we always pick such a subsequence? So And you can just filter out the values of the sequence, like maintaining a local a local maximum. You say this is a local maximum. You say x equals m equals to x1 initially, and you consider x1 to be inside your subsequence that you are constructing. Then you traverse the subsequence. When x equals to x1, you iterate to x2, that if x1, sorry, x2 is greater than m, which currently is x1. If it's not greater than n, then you don't take it, and if it's greater than n, you take x2 and you update the value of n to x2. And when you continue, like, you will be able to, until and unless you reach the maximum value of the sequence before completing this task, because maximum value of the sequence is xk, and it's somewhere like you reach that xk pretty soon, physical. And of course, you can't increase the sequence further in that case. So then you can just repeat uh, you say the, yeah, then we can just remove xk from our sequence. Whatever, after we have got a monotonic subsequence, then from the conversion, the monotonic convergence theorem, that subsequence is both monotonic and bounded, so the original sequence is bounded. So it's convergent also. It's not convergent parameter, it's called density. So let's see an example now. So let's look at the sequence 1 plus 1 by n whole power n. So as you know, limit of x tends to infinity 1 plus 1 by x whole power x is e. Correct. So let's see if the simplicity converges to that Euler number e. You want to say the monotone convergence curve. And you have to first show this is monotonic. Let's see if this is monotonic. So 1 plus 1 by x whole power x. So let's see the x. To differentiate it, it's uh, so that I guess we could take e, which is e to the power x times log of 1 plus 1 x. Right. Now let's differentiate that. This is e to the power x. So e to the power x is the same thing times log of 1 plus 1 by x plus x times x by 1 plus 1 by x times minus 1 by x squared. this is 1 plus 1 by x power x times log of 1 plus 1 by x minus 1 by x plus 1, 1 by x plus x. So this thing I want here, the first product term is positive. Between the second term, the log of 1 plus is x plus 1 by x times of x by 1 plus x minus of you can write 1 minus x by 1 plus x minus log x by 1 plus x minus 1 plus x by 1 plus x. It's x by 1 plus x minus something like this one. Okay, it's kind of difficult to predict it like that. So let's see if we can do something. Say 1 plus 1 by n whole power n. Says so if you take 1 plus 1 by n, 1 plus 1 by n, 1 plus 1 by n and 1, so it n times, and n times 1 plus 1 by n is greater than or equal to 1 plus 1 by n whole power n minus 1. This is n plus 1 third. I was having more. So n n plus 1 plus 1 If I do it n plus 1 times still one by plus 1 plus 1. So this is n plus 1 plus 1 by n plus 1. One by we need to show 1 plus 1 by n plus 1 whole power n plus 1 greater than 1 by 1 plus 1 by n whole power n. That sorry, there's a whole 1 by n plus 1. I think the geometry means obvious. So that's what this word means. So that implies 1 plus 1 by n plus 1. We take 1 n plus 1 whole power both sides. This is from AMGM. Therefore, this is xn plus 1 and this is xn. So xn plus 1 is greater than or equal to xn. Therefore, xn is monotonic. Increasing sequence. And the one other condition that we need is boundedness. Why is the sequence bounded? Well, xn is equal to, if we take the binomial expansion of 1 plus 1 by n whole power n, we get 1 power n plus nc1, 1 by n, nc2, 1 by n squared, up till ncn, 1 by n power n. Okay. So this is 1 plus n, nc1 is 1, and n by n is 1. nc2 is n minus 1 by n, which is 1 minus 1 by n. there is a 1 by 2 outside, like that. So we will get 1 minus 1 by n, 1 minus 1 by 2 by n, the last term, 1 minus up to, not 1 minus, up to 1 by n, this whole thing divided by n. Just multiplying 1 by n to the power t to the above following factorial. N minus 1 n minus 2 up to 1 becomes 1 by 1 minus 1 by n, 1 minus 2 by n, 1 minus 3 by n, up to 1 by n. Right. So, see how this is 1 1 by 1 factorial plus 1 by 2 factorials times something that's less than 1 plus 1 by 3 factorial times something that's less than 1, like that up till 1 by factorial times something that's less than 1. So we can say this is, it's less than or equal to 1 plus 1 by 1 factorial plus 1 by 2 factorial. So instead of multiplying things with less than or equal to 1, I'm multiplying them with 1, so I'm getting something larger. And this sequence is basically the expansion of, so as I mentioned, the sequence is the Taylor expansion of e to the power x at x equals to 0. So it's e to the power 1. So therefore e is and not is the supremum and x bounded. Therefore by MCT xn converges to e and then comes to input. Another sandwich theorem. So if you have three sequences, x and y and z, and all the three are two of these converge. So xn converge to L, and yn also zn also converges to the same point at L. Then we can say, and also xn less than or equal to yn less than or equal to zn for all n matches. They're kind of sandwiched. Yn is kind of sandwiched between xn and yn. So the theorem says then yn also converges to L. So it's kind of the sandwich, equivalent to the sandwich theorem in calculus. The proof is implies from the triangle inequality, like you can say yn minus L less than or equal to yn minus xn plus xn minus L. Less than or equal to, since yn is smaller than zn minus xn plus xn minus L. And this goes to 0 as n tends to infinity. So this is xn minus L. And since xn is tends to L as n tends to infinity, this is basically less than epsilon. Epsilon fixed epsilon. So yn minus L is less than the left side, so minus convergence. O enter is to L also. Okay, so let's solve some examples and problems. So try to show n minus 1 by n plus 1. The sequence converges to 1 from the basic definition of limit of a sequence. Then part 2, try to show the same for square root of n plus 1 minus square root of n. And this is equal to how much that also you have to calculate. Okay, we'll be back in 5 minutes. Okay, so the first one was a lot easier. So if you use the principles of normal limits, you can just divide by n on both numerator and denominator. Get 1 minus 1 by n by 1 plus 1 by n, and both of them tend to 0 as n tends to infinity, and you get 1. But that's not from the, the basic definition of sequence. So let's see. So xn equals to n minus 1 by n plus 1. We fix some epsilon positive. So finally, we want to find some. So we need to find n, in naturals. And this n it can depend on epsilon, such that for all n greater than that n, we have, so the limit here that we need to show is 1. So 1 minus n minus 1 by n plus 1, this has to be less than epsilon. So let's try to simplify this. So 2 by n plus 1 has to be less than epsilon. We no longer need the mod since it's already greater than 0. And then we can take, observing that this 2 by n plus 1 is strictly decreasing. So we can take n to be equal to, let's say 2 by n plus 1 is less than epsilon if and only if 2 by epsilon minus 1 is less than n. So we take n equals to ceiling of 2 by epsilon minus 1. And that n works. This also depending on epsilon as we first hypothesized. So this was the first problem. For the second one, so we have root over n plus 1 minus root n, and we don't even know the limit. So xn is root over So as you can guess by looking at this that the limit might be 0. since for a very large number that plus 1 makes almost insignificant difference. So try to show xn goes to 0. So for that we again fix epsilon positive, and finally we need to find some n epsilon such that 0 minus n plus 1 is less than that. So this is equivalent to again this is positive, we can ignore the mod signs. Now we can rationalize. We again find this to be monotonic decreasing, so capital N plus 1, capital N. Or we can make it even simpler. So this thing is less than 1 by twice root over n, right? So we can take twice root over capital N less than epsilon if and only if 1 by twice epsilon whole squared is less than n. So we can take n to be equal to ceiling of 1 by 4 epsilon squared. So we are done. Okay, so next, oh, by the way, this is for sequence. So there are things called series. So what are series? Series is basically the it's a sequence where the terms can be represented to have been taken from us underlying sequence. Like, say, suppose S1 is 1, so call it X1. X1 is 1, X2 is 1 plus 2, X3 is 1 plus 2 plus 3, X4 is 1 plus 2 plus 3 plus 4, like that. So you have Xn is equals to 1 plus 2 plus up to n. So this is basically a sequence which is where Xn is equal to n into n plus 1 by 2. But if you think in terms of these terms that are getting added up, this is a series with the corresponding sequence as the terms. So for every sequence, you get a series which we call the partial sum series, the series of partial sums. And okay, so the next limiting theorem that we will study is called the Cauchy's convergence criteria. Cauchy's convergence criteria. There is something called the Cauchy sequence. So let's see. So a sequence xn is called Cauchy. Yes, the sequence, there is no particular sequence that is given by Cauchy, so it's called Cauchy sequence or like that. It's a property. So Cauchiness is a property which a sequence acquires when this following condition is true. If and only if for all epsilon greater than 0, nm greater than some natural number capital N implies the difference between xn and xm is less than that epsilon. If this happens, then you can see like you can bound the adjacent differences between the the simultaneous terms of a sequence by bounding their indexes, right? So this property is called Cauchiness, and for real numbers, this property actually implies convergence in a sequence. For that is what is called the Cauchy's convergence criterion. For reals or some complete finite fields like real numbers, we have Cauchy sequence are all convergent. Actually, this is an if and only if condition. A sequence is Cauchy if it's convergent. A sequence is Cauchy if and only if the sequence is convergent. Proof. You already know what is a convergent sequence, and already you just saw what is a Cauchy sequence. Now we have to find the if and only if part, right? Let's do the if part first. So if part, that we already know the sequence is convergent. We have to show it's Cauchy. So we have a sequence xn that converges to x. Now let's see what the difference xn minus xm actually is bounded by. So that difference can be written as xn minus x plus x minus xm. And right, so this is using triangle inequality. Triangle. I mean, sorry, this is not equal to, this is greater than or equal to. So xn converges to x implies the difference is bounded by these two values. Now you see, the limit is x, right? So after some n, this difference is less than epsilon. Okay, so let's take, so there exist, so first we have to fix epsilon, right? So fix epsilon positive. There exist capital N1 inside naturals, such that mod of xn minus x is less than epsilon for all n greater than n1. And there exist, sorry, they call epsilon by 2. Okay. Right. Okay, that should do. So now we have xn minus xm less than or equal to xn minus x plus xn minus x. And since we are under for all n and m greater than that n1, so both of them are just from this less than epsilon by 2 and epsilon by 2, and they add up to epsilon. Right. So xn is Cauchy. Right, so we have shown one direction. Now the other direction, the only if part. For the only if part, so we take a Cauchy sequence xn. So let xn be Cauchy. Now we need to show it converges. So first, let's see what's the definition. Well, the definition is that. Okay, let's first try to show the sequence is bounded. If we fix epsilon to be equal to 1, then there exists n in capital, capital N in natural such that for all n greater than n, mod of n minus am is less than 1. Right. Thus, we can say now mod n is equal to mod of an minus an. Sorry, I'm writing a here. Okay, let's call the sequence a and then instead of x. An minus a capital N plus a capital N is less than or equal to from triangle inequality an minus a capital N plus an, and this is less than or equal to 1 plus an, since sorry, this is 1, this is not equal to 1. So everything after capital N is bounded above by 1 plus an. So we can take the upper bound L to be equal to max of A1. So before capital A, capital N, there are finitely many terms. So we can define a maximum for them. Right. So if we define L to be the maximum, then for all n and n, an is less than L. Right. Therefore, L is the upper bound of n. So n is bounded above. So by Bolzano-Weierstrass theorem, there is a subsequence of this sequence called this ANK, which is convergent and monotonic. And say suppose it converges to some limit a. We don't know it yet. Now we have to claim the whole sequence converges to that limit a. So how to show that? Well, we now we evoke the Cauchy property. So we'll fix epsilon first. So fix epsilon positive by Cauchy's property. By Cauchy property, there exists N2 in N. So the difference between what did I call the sequence? A and K, right? Difference between A n minus AM is less than epsilon by 2. Epsilon by 2 for all nm greater than n1, n2. So that n2 exists. Therefore, so on the other hand, since we have that subsequence A and K that converges to A, so we may so there exists N3 inside naturals such that for all nk, for all k greater than n3, mod of a minus a and k is less than epsilon by 2. Okay. And you observe that if k is greater than n3, then obviously in the original sequence, cannot obviously, let's see. So we can now write a n minus a to be equal to a n minus a n k is not equal to, this is less than or equal to, let's say n k minus a. This is epsilon by 2, strictly less than epsilon for all n greater than max of n1 and n2. So you see the idea is you have a subsequence that is, yeah. So terms of that subsequence can be made as close as possible to A. So we can make it, we can keep it closer than epsilon by 2. And other terms we can, since they are Cauchy, we can make those terms closer to A and K by another epsilon by 2. So that overall, the maximum distance between A and A is epsilon. And that's enough to prove the sequence is convergent. Therefore, n converges to A. So both if and only part are proved. So Cauchy sequence is equivalent to a convergent sequence when you're dealing with real numbers. Okay. So I guess that's all for today. Thank you all. Meet you next week. Bye.